So before I start my presentation, I must thank the organizers for giving me an opportunity to speak to you about my research work in this online summit on Optics and Photonics 2020. So I must thank Praveen Pothala, President Destemio Singapore, and the organizers and the team behind you who is taking care of everything in this seminar. Unfortunately, we are not meeting face to face, but in this COVID-19 pandemic era, we have to have some solution like this, and we are forced to do these kinds of arrangements. So I shall be discussing about my research work, which is optical cryptography. So I'm basically from Indian Institute of Technology, Patna, which was started in 2008. You can see the building which is coming up, and many more buildings are coming up. So in this seminar, I shall talk about optical cryptography or optical crypto system. Then in optical crypto system, then as in general in digital techniques, we have digital crypto system as well as optical crypto system. So similar to the digital crypto system, in optical cryptography also, we have two types of encryption schemes: symmetric crypto system as well as asymmetric crypto system. I shall devote more time on asymmetric crypto system, which is a better kind of cryptography. And some of the recent results based on the QR code, quick response code, and interference based, and also actually optically implemented the quick response code and exclusive OR operation. And the most important thing about these schemes, what I'm going to talk about, is that we have implemented it not using a laser, but using LED light source, which is much cheaper, and it is a kind of alternative system to the existing digital crypto system, which we envisage that in future people will be utilizing this kind of crypto systems. And in any crypto system, it is important to talk about the analysis or the security strength of the system. So we do cryptanalysis, and at the end we will conclude. So information system, as we talk about, it is how do we define it? Optical crypto system is to protect information or data from unauthorized use or counterfeiting. In crypto system or information security, we have encryption as well as decryption. So optical encryption schemes are better than digital techniques. Why it is better? There are several degrees of freedom associated with the optics, which we can utilize in such crypto systems. Like processing is done in parallel. Optics does the parallel processing as compared to the digital domain, where it is the serial processing. Speed is undoubtedly much better in optics, or nothing can beat optical speed. It offers unauthorized access to the data, and several degrees of freedom, including amplitude, phase, wavelength, spatial frequency, polarization, orbital angular momentum. These are the various degrees of freedom which we utilize in designing the crypto systems, which is purely based on optics. So let me go to the history part of this story. It started in 1995. What you can see on the slide, that there was only one or a few research publications which appeared in 1995, and since then it has been linearly growing, the number of publications which are coming in, and creating lots of research analysis on this particular topic. So you can see this is only 25 years old study, and it has attracted lots of attention to the international scientists across the globe. So what is the basic of the encryption system or optical encryption system? What we do, we start with an input image or input data, whatever you have, and we encode it with the input phase random phase mask, which random phase mask is a purely phase function, and it has random value. And this input function along with the input random phase mask is placed in the front focal plane of this lens, which will do the Fourier transform if we utilize coherent beam of light here. In the Fourier plane, we place one more random phase mask, which is basically a replica of this input phase function, but they are independent. They are different. So all the phase masks in the encryption schemes, what we use, they are unique basically. You cannot counterfeit the one phase mask with the other phase mask. It is really a random phase function. And then this one more Fourier transformation of this input function will give you the bring you to the image plane. So obtaining two Fourier transforms in series gives you the image back. But in this case, the image, what was the input image of a Lena, it doesn't remain same. It gets modulated due to these two random phase functions, and what we get is then white stationary white noise, and this white noise we call it as the encrypted image. This is the whole fundamental principle of this optical cryptography or optical crypto system, what we call as the double random phase encoding. So this started in 1995, the first paper by Professor Bahram Javidi and Philip Refrigier. So this came in Optics Letters. So we are using two random phase masks, one in the input plane, other in the Fourier plane. And this input image is encrypted into noise-like image. Knowledge of these two phase masks are key to the retrieval of the data. So this is the basic scheme. And for retrieving, we have to retrace the whole story, retrace the whole path, and we can get back the original image. Now, this kind of cryptography in which we need to use two random phase masks, and both the random phase masks are needed for retrieval of the data. So it is a kind of symmetric crypto system. So the encryption key and the decryption key are same. So we came up with another idea, what we call as the asymmetric crypto system. So in symmetric crypto system, as I mentioned, the encryption keys are same as the decryption key. You don't have different keys. But in this case, because the whole process is linear, it becomes vulnerable to the security breach. So we have to come up with the new idea that how we can counter those security issues. So we came up with the asymmetric crypto systems idea, in which encryption keys are different than the decryption keys. How they are different? Let me explain that. That suppose we start with this input kind of input image. We have one random phase mask, what I'm calling it as the encryption key 1. You multiply this input image with that encryption key 1 and calculate its Fourier transform. In the Fourier plane, which is basically a complex function, we segregate the real part and imaginary part. Or I can say that amplitude and phase parts are separated. And we store the phase function and process the amplitude function. So what we have stored here during this process, stored the phase function, we are calling it as the decryption key. And with the leftover the function, we again multiply with the one more random phase mask, what we call it as the encryption key 2, and compute one more Fourier transform. It gives you this encrypted image. So what we have done, like previous case, we are using two random phase masks, one along with this input image, another in the Fourier plane. But during the process, After each Fourier transform, we have separated the real and imaginary part, or the amplitude and phase part, and stored the phase part and processed the amplitude part only, what we call as the amplitude truncation and phase truncation. So finally, what we get is the encrypted image. So to get this encrypted image, we started with two random phase functions, encryption key 1, encryption key 2, and during the process, we stored two keys, what we call them as the decryption key 1 and decryption key 2. Now, for retrieving of the data, what we call as the decryption, what we have to do, we have to reverse the whole process, start with encrypted image, multiply it with the decryption key 2, and take the Fourier transform, again do the phase truncation, multiply it with the decryption key 1 here, and finally what you get is the decrypted image back. So we started with the original input image, and we have retrieved this image back here. This is what the whole story is. Now in this process, what we have seen, that we do not require the use of encryption key 1 and encryption key 2 during decryption. So that is why we call them as this is asymmetric crypto system. Here the encryption keys are different and decryption keys are different. And this is what it gives you the result. So this encryption scheme is much better as compared to the symmetric crypto system. So if we compare the difference between the symmetric and asymmetric crypto systems, symmetric crypto system is a linear system, asymmetric is considered to be a non-linear system. Symmetric crypto system, we use the same key for encryption, but in asymmetric crypto system, we use different keys for encryption and different keys for decryption. Symmetric crypto systems are vulnerable to attacks such as known plain text attack, but asymmetric crypto system resists known plain text attack. Examples are DRP, what we call as the double random phase encoding, and the derivative schemes. And asymmetric crypto systems, we call them as the PTFT, what we call as the phase truncated Fourier transform, and EMD based. EMD stands for equal modulus decomposition based schemes. What is EMD is in the Fourier transformation, in this Fourier phase truncation, this phase and amplitude part is different. So we can equate them using some factor. This is what we do in the equal modulus decomposition method, and that improves the efficacy of the whole system. In addition to that, in this case, to add more features and make it stronger, we have applied phase retrieval algorithm. In phase retrieval algorithm, as the statement says, that we wish to determine the phase of a pair of light field distribution related by Fourier transform if their intensities at the respective optical planes are known. Or in another way, determine an unknown object function gxy from the magnitude capital G fx fy of its Fourier transform. So you have a function, obtain its Fourier transform, and take the intensity of that Fourier transform. If you record the intensity of the Fourier transform, if you wish to retrieve the original function back, you cannot, because while recording it as the intensity function, you have lost the phase function. So this phase retrieval algorithm helps you retrieve that lost phase function, and you can get back the original image or original function. So this phase retrieval problem, this has helped in creating various kinds of optical crypto systems. And this is known as the basic theory was given by Gertzberg and Saxton in 1972. So this is called as the Gertzberg-Saxton algorithm. This algorithm has been further added with the hybrid input-output algorithm as well as the error reduction algorithm. So that improves the quality of the input image while doing this phase retrieval. So we have combined this phase retrieval algorithm also with the encryption system. I'll come to that point. So this is the algorithm. We start with the random phase function. You start with the object domain amplitude. use a new phase function, multiply by that phase, to obtain the Fourier transform, compute phase only function, and you keep on iterating every time till you reach to the desired function. This is what the algorithm is. So it is an iterative algorithm, and it takes time in while computing the phase function. Further, what we have added is the QR code. And the quick response code, as you know, it is a matrix or a two-dimensional barcode, first designed for the automotive industry in 1994 to hold information. So basic purpose of the QR code is that it holds information. A barcode does also holds information, but barcode has very less storage capacity. On the other hand, QR code has enough storage capacity. We can store enough information as compared to the barcode. So this is and this is basically a binary function. So it resists lots of noises. So this is a very good feature what we can combine in the optical cryptography. So this is what we have done here. So there are 4 standardized encoding modes for the QR code. They are called as the numeric, alphanumeric, byte binary, and kanji, because it has been developed by a Japanese scientist. So this name is there. So we applied this QR code and the optical interference based asymmetric crypto system. So as I mentioned, that asymmetric crypto system is much better form of the cryptography. So what we have done here, that we have started with an image encryption scheme where we have combined QR code and interference, and we have done it in the Fresnel transform domain, not in the Fourier transform domain. And Fresnel transform domain, it offers additional features like the wavelength of the light source and the distance propagation parameters. They are the additional features which helps in getting better features of the encryption system. So input image is encoded into 64 QR codes, which are tolerant to external noise and partial data loss. Analytically, we generate phase-only masks that have been used to ease the problem of storage and transmission. And further, we have applied the Arnold cat map, which randomizes the organization of the pixels, and that helps resolve the Silhouette problem. And it is also immune to the existing attacks. So what is an Arnold cat map? It is a basically two-dimensional invertible chaotic map, which when applied to an image, it randomizes the original organization of pixels. Period of the Arnold cat map is determined by the number of iterations. So 2D cat map is defined by this expression. Map is an area preserving map, since the determinant of A is 1. And Arnold transformation of an image is given by this TXY, which is AR IXY. So Arnold transformed image is divided into n equal size matrices, and each matrix is encoded into a QR code. Thus, we obtain n number of QR codes. This will be clear from this scheme. So this is your input image, and we apply the Arnold transformed image, and then we have created n number of blocks, division into n blocks, and each block is encoded into a QR code. At the end, because QR code is a binary function, we can combine all of them, so it becomes a matrix, binary matrix. This binary matrix, we make it a complex function, and this complex function we have to truncate amplitude and phase. So we have applied interference-based scheme. What is that interference-based scheme? Is this one. Suppose I start with a function h xi eta. If we multiply it with the phase function exponential I to pi xi eta, so then we obtain a new function h prime xi eta. Now this h xi prime eta, h prime xi eta can be expressed into two phase only functions like exponential I m1xy and exponential I m2xy, and they are basically convolving with a function hxyl. So in this way, we can convert this one complex function into two complex functions, and what we call them as the phase only masks. So this is what is obtained here. M1xy and M2xy can be obtained by these mathematical expressions. This is done analytically. So our main idea is that we have this function h xi eta, and from h xi eta, we want to obtain two phase only functions, and these two phase only functions are M1 and M2. And this is what we apply here as P1, P2 or M1, M2. This is what we call as the interference-based optical encryption. Now for retrieving the original information, what we have to do, we have to start from this part M1, M2 to get back the original input image. So some of the simulation results, like this is the input image, and we have applied the Arnold transformation. Like when applying the Arnold transformation, we have 1 iteration, 5 iteration, 10 iterations, 100 iterations, 1000 iterations. So that we decide how many iterations we have to apply. Depending upon our requirement and the need, we can select how many iterations are needed. So then these are the two phase only masks, P1 and P2 or M1 and M2, whatever we call. So these two phase only masks we have analytically created, generated, and while applying these two phase only masks, following all the processes which I showed in this algorithm flowchart, we have to retrieve the full this process, and we obtain the original image back. And if there is any mistake while computing the reverse process, and any of the phase mask, any of the phase functions is wrong, then we cannot retrieve the phase function, the original image back. So this is the beauty, and this is the strength of our crypto system, in which we have used, and it is much resistive to noise. We have taken a screenshot because QR code you can utilize with your mobile phone camera. You can utilize your mobile phone camera where you have this QR code scanner. This is what data you will get. So as I mentioned, we have created 64 QR codes in this process. If you can retrieve data with 8 QR codes, 16 QR codes, or 32 QR codes, it means if you are using less number of QR codes, then you will be retrieving the data. If your other parameters are correct, you will be retrieving, but you will be retrieving only the partial information. So if you have 8 QR codes, this much information you will retrieve. 16 QR codes, this much information you will retrieve. 32 QR codes, this much information you will retrieve. And what I am showing here is one of the QR codes out of 64. This is 25th QR code. So we had created 64, and I'm showing you only one QR code here. So we applied the attack analysis to check whether this is a strong technique or not. So this is what you can see, and with the plot, it shows the percentage of pixels of the phase only mask. P1 is known to the attacker. P1 is known to the attacker, but P2 is unknown. Then what is the CC values? CC values means this is a cross correlation values, but you can see it is always very less. Like it goes maximum to 0.14. Typically, it should go to 1. Then only it will be decrypted correctly. And this is what you can see, the decrypted images of the net by the attacker for a percentage of pixels of phase only mask P1 is known. So if even if 99% is known, it cannot be decrypted. So this shows the strength of this crypto system. As I mentioned, that QR code is noise resistant. So we studied the effect of the noise. So noise analysis here, you can see using Arnold cat map and 5,000 contaminated pixels. Here it is 19,000 contaminated pixels, and this is without using Arnold cat map, but and 19,000 contaminated pixels. Accordingly, you can see the results here. This is the statistical analysis, histogram of the original image and histogram of the analytically generated one of the phase mask, which I am showing for the reference. So this was one scheme where we utilized quick response code along with the this interference-based scheme here. So next scheme is that when we are applying this QR code with the incoherent illumination. Incoherent illumination means, or it is partially coherent illumination, we are using LED light source, not a laser light source. So this is what I'll explain. So we have applied the optical XOR operation, exclusive OR operation through completely optical means. So for this, we have utilized two spatial light modulators where the optical interface device, electro-optic devices. Like we are displaying some gray value on the SLM1, some gray value on the SLM2, and we are trying to obtain this exclusive OR operation. This is what you will get after XOR operation. This is the actual experimental setup, very easy, but it has very tricky things, like we have to use two SLMs. So using two SLMs, and these are some of the results for the exclusive OR operation, combining it with the two SLMs, like QR codes, and you are applying the exclusive OR operation. These are some of those preliminary results based on that. So in actual implementation it for the security system, so these two SLMs, they have to be pixel to pixel match. SLM is a pixelated device, and these two pixelated devices have to be matched pixel to pixel. So there should be very good alignment is required here. Otherwise, the experimental setup is very easy. The only tricky part is the alignment of two SLMs, which are basically which have to be pixel to pixel match. And then you can obtain this whole experiment. You can do the whole experiment. So encrypting QR codes with the XOR operation, QR code, which is basically binary image, which denotes by logic ones and zeros. Each pixel of the QR code undergoes XOR operation with the random binary image. This is what you have. QXY, and it goes with the XOR operation with the KXY. And for decryption, you have to reverse it. Then it becomes very easy to obtain. So I'll show you some experimental results. Like this is the plain text encoded QR code. This is the encryption key, and this is the encrypted image. So I'm showing one of the QR codes, not all. And these are the results. And the very important thing about the results, what is to be noticed, that I'm showing the results with the green LED. Green LED, it is the decrypted QR code with incorrect keys. This is with the correct keys. This is incorrect keys. You can see that original information is not decoded correctly. This is decrypted QR code with correct keys, but here it is done with the white LED. And the last result is with the laser source, 532 nanometer wavelength. DPS is laser. So here you can see it is much noisy. And this is what we want to emphasize, that if we are using a LED source, which doesn't carry much noise, and QR code is much noise resistant, but it doesn't work well if we are using a laser source. So we have done the analysis also, and we have shown the comparative results with the light source and the cross correlation values and the mean square error. Ideal case cross correlation should be 1. and mean square error should be 0. For the green LED, the value was 0.93, MSC was 0.16. For white LED, it was 0.91, and MSC was 0.17. Laser, it was 0.89, and MSC was 0.28. So as it is evidenced here from this data, that laser source is not very useful in this case because it is introducing noise, as the speckles are the very well noise created by the laser. So further, that was for the binary data. Now we have applied it for a color data or color information. And here we have added the polarization part, polarization encoding using the pair of the liquid crystal based SLMs. This part I will skip because it is the phase retrieval algorithm, which is the same which I mentioned in the beginning. So encryption procedure is like this. You have the plain text color image. As we know that plain text, the color image has the 3 components, red, green, and blue. So this red part and green part, so we transformed into the PVDs and decomposed into bit planes, each one red, green, and blue. And then we applied this XOR operation and randomized with the QR codes. All bit planes of the XOR operated images are then combined. So we have this K, RJ, K, GJ, K, BJ, and at the end we combine them, and what we get is the key KXY. And here we have the ciphertext QXY. So QXY and KXY, which I showed you here, this is the same principle we apply for obtaining the encryption. Here we have the steps are added, or steps are more because of the color pattern. If it is binary, then those steps will go away. So these are some of the simulation results. Like this is the plain text image. This is the red component. So from the plain text, which is a basic, we can rate color image. You can segregate the red, green, and blue. I'm showing you the results with the red component. This is the phase value decomposition, PVD. This is one of the bit planes of the phase value decomposition, one of the QR codes, and XOR operated image, and apply everything correctly. And this is what is the decrypted image you can obtain. So experimental results, this is the light field image. This is a light field image for QR1, and this is XOR operated. This is the key what we have obtained with the XOR operated image. We have applied the more security analysis, that if some of the or the partial information is lost from the data, what will happen? What you can see here is the conventional XOR operation. This is the proposed method here. So some portion of the information is partially, the information is lost. Still we can recover, and we have 90% here, 44%, 22.7%. Still we are able to recover, but partial recovery will be there. As it is more noise resistant, so some results on the noise analysis. So I hope I have not taken much time to conclude. I have discussed an optical asymmetric encryption schemes based with the quick response code and interference, and further with the applying this phase retrieval techniques. Phase retrieval techniques basically improves the effectiveness of the exclusive OR based encryption technique, and we demonstrated with the partially coherent illumination and QR code and XOR operated again for the color image encryption. So that is all from my side, and to let me know the audience, I have authored a book which is Optical Crypto Systems. This is the first book on the crypto systems which deals only the optical techniques. It was published by Institute of Physics UK. It published on 31st of December 2019. ebook, and the hard copy is also available. So those who are interested, you can refer to this book. And I must thank everyone, whoever is attending my seminar here. This is my laboratory. Thank you so much for your kind attention. And if you have any question, please feel free to ask me. I should try my level best to answer your curiosity or questions.